So I gave this talk in Paris at the ICMRM. Larry was there, and I hope nobody else was. Anyway, and I've worked it over a little bit. So I'm going to tell you about how NMR was done before silicon, before computers, before transistors, because that's the first instrument I built. And what that means is no signal averaging, no Fourier transform, right? And then you wonder, well, you know, what the heck could we have done? And what I want to tell you is that if you read something like Bloomberg and Purcell and Pound, which is published in the 40s, a lot of NMR that the principles are all there, right? I mean, what's phenomenal is that those guys in the 40s sort of figured out in the framework anyway of the NMR as we know it today. And in some ways, all we've done is to refine it. That's not quite true, but it's sort of true, which is just astonishing, right? And so the fact that Bloch and Purcell got their Nobel Prizes in the 50s is absolutely merited. And so I did my construction and experiments in the 60s. I gave this talk in Paris, and I realized in retrospect that, you know, you'll see, I mean, I described the equipment and tried to emphasize the fact that there are no transistors involved and whatnot. But looking back on it, I didn't make it dramatic enough, right? Because I gave the talk as if here's the instrument, here's the way it works, here's an NMR signal and stuff. It's all matter of fact. And you guys are, you know, the people in the audience just go home thinking, he gave another NMR talk. And so what I should emphasize is how primitive that system is compared to what we can do now, and exaggerated even, to hammer home the fact that it was indeed, you know, a very primitive instrument in terms of its computing power, which was 0, right? And even like making a counter that counts up to 16 was a big deal, because it took 8 or, well, with impedance matching, maybe 12 vacuum tubes, which are this big around and this tall, and you drill holes in a chassis, and the chassis ends up this big, right? 17 inches wide and things like that. So it's unimaginable for somebody learning NMR now how primitive things were. And I want to sort of tell you how things were done. And then you can actually go back in the literature and see how much good NMR was done in those years without any of the modern trappings. So, a lot of these things happen triggered by something. So I used to do a lot of mountaineering, and I was fortunate enough to be in a group that made the first ascent of the highest mountain in Antarctica in 1966. And the reason I'm telling you this is that in the early 60s, the group I was in, which was based in Seattle, was not the only group that thought of going to make the first ascent in the highest mountain in Antarctica. At the same time, there were several other groups, including a main one that was based in Eastern United States. And those things don't happen in the vacuum. It's sort of like the NMR starting at Harvard and Stanford at the same time. There's some event that triggers things in people all over the world at the same time. And this was the International Geophysical Year, which happened 6 years earlier. And there were these fabulous pictures of tall, wild-looking mountains in Antarctica that no one had ever dreamt about. And so then people start thinking, oh, well, we should try to go there, blah, blah, blah. And then simultaneously, right? And so that, I mean, most of you know that NMR started the successful NMR experiment. People thought about doing NMR in the 30s, and they failed for reasons that we don't have to go into now, but they're very instructive. And then after World War II, all these people came out of the war with various experiences, and there's a set, not trivial number of people who worked at the radiation lab, which resulted in multiple volumes of scientific instructions on how to make things. And one of them was radar technology, and the group of at Harvard and group at Stanford came up with doing NMR. And at first, it wasn't even clear to most people that they were the same experiment. They were related experiments, because Harvard did the marginal oscillator NMR. So you make an oscillator that barely oscillates, and then when you go through resonance by changing the magnetic field, the loading of onto the tank circuit decreases the amplitude of the oscillation of this marginal oscillator. Whereas Stanford did an induction experiment, so they actually measured the magnetization rotating in a coil. Well, if you think about that, they're totally different experiments, right? I mean, what you find out is different. In one case, it's sort of a spectrum, and the other case, it's the behavior of the spins at resonance. And it was to the credit of the Physical Review editors that they recognized that these two manuscripts are sort of two sides of talking about two sides of the same thing, and they got published in the same issue of Physical Review, which is just, it's pretty astonishing right there. So let me go through a brief history and I'll give you some examples. So all these guys came out of Second World War, and they knew about radar, and then the group at Harvard thought of doing this as a marginal oscillator. The group at Stanford did it as an induction experiment, as we all know. And I got out of University of Chicago in 1957 with a liberal arts degree. So Chicago was famous in the late 40s and early 50s for an undergraduate degrees that had no electives involved. You just took 4 years or 3 years of humanities, 3 years of social science, 3 years of natural science and some other stuff, and got a degree in liberal arts. And that was started by Robert Maynard Hutchins in the 30s. And by the 50s, the university administration recognized that it was not very popular, right? Because at the end of that curriculum, in some ways, we still didn't know anything. I mean, we just knew a lot of little bit of things. Like in sciences, we'd read Galileo and Newton, but we wouldn't learn anything modern. We're learning about the thought process that goes into doing science, and in the humanities and social studies, the same thing. And even though they encouraged high schools to encourage good students to come and apply to go to the University of Chicago on that liberal arts degree after their sophomore year in high school, most high schools were reluctant to let their good students go at that level. So the program suffered. When I went, undergraduate enrollment at the University of Chicago was something like 1,400. It's over 5,000 now. So, I mean, it's interesting to see a university administration try to decide in what direction they should go. And the University of Chicago was kind of oscillating between an academic idealist for a while, and then they put a business person in to try to, grow the enrollment again, then go back to the academic thing, and it was kind of oscillating for a while. They seem to have hit a very nice compromise now, and the undergraduate body is now finally bigger than the graduate student body, which has always been like 5,000. There was outstanding, blah, 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 right? So I graduated from the college. I had come to the United States when I was 13, which is in 8th grade, and I went to the University of Chicago starting in 11th grade. So I had a hard time learning English, and I just struggled at everything except maybe math. And so when I got out of the University of Chicago in 1957, and I was kind of on my own. I had a guardian in the US, but they were very busy. And so I just kind of, after the first couple of years, I put myself through college by working at various jobs and whatnot. And it never occurred to me what I should be thinking about what to do after I graduated from college. So that spring, after I discovered that all my friends had made arrangements to go to various graduate schools, I thought I should do that. And it was too late to apply for any fellowships, but somebody said, oh, you should, you know, that bulletin board over there has a notice from Dartmouth College for something called Teaching Fellows. And it's a 2-year terminal master's degree program, but you know, Dartmouth is an undergraduate college, and so they had to create this artificial terminology, I guess, to have teaching assistants. And so I applied and got in. And my thesis advisor is Bob Christie, whose 97th birthday I celebrated with him last Saturday in Hanover. So I went to Dartmouth for 2 years and studied. I wrote a master's degree in ionic conductivity, and not something like, you know, sodium chloride color centers, and I created the color centers in a hospital X-ray machine, and I bleached it thermally and measured conductivity and whatnot. And that's when I really learned about physics experiments, right? Because at University of Chicago, I did the liberal arts stuff. I have a secondary bachelor's degree in physics, but I didn't really know. Basically, what you do is add some course record on top of the liberal arts BA, and it's pretty minimal. So I still didn't know anything about physics when I got to Dartmouth. So I consider my years at Dartmouth to be the one where I really learned to become a physicist. But I was still kind of just barely keeping my head out of water. So when I left Dartmouth for a summer job at Argonne, I still didn't have a plan for the future. And when I was at Argonne, there was a guy, Gil Perlow, who'd just come back from a sabbatical at University of Washington. And I was asking around, you know, I want to go to graduate school. Where shall I go? I want to go somewhere where I haven't been. And so Gil said, well, go to Seattle. University of Washington has a pretty decent physics department, and you like to go hiking and climbing, and there are lots of mountains out there. So I went, right? I called him up. Oh, no, I didn't call him up. In the 50s, you didn't call people up. You wrote letters. And those are things on paper. And they wrote back and said, we don't have any assistantships anymore because it's too late, but we have a stockroom job. Things are really informal because I'm not sure that I sent him a transcript or anything, right? I just wrote that I just got a master's degree from Dartmouth. And so I told them, I'm coming out. And I drove out there at the end of September. Washington was, I have the peculiar experience of having gone to 3 institutions of higher learning, and they were all on the quarter system. And so at the end of September is when school started, and I drove out there in September. And then when I arrived, they said, oh, somebody resigned his assistantship, so you can have it. Right. So I landed on my feet all right. And then I met up with Henry Silsby, who had just come there from University of California system, where he was involved in measuring magnetic moments of neutrons and other ions at a beam experiment with Nuremberg. And he was really a neat physicist, and I liked him, so I signed up to be in his research group to do molecular beam experiment. And he had us making a cyclotron as a kind of a mass spec device and / detector for the molecular beam experiment. So we're going to lead a molecular beam into the middle of the cyclotron, and there was an electron beam that ionized it. And the things with a right a charge to mass ratio would get spun out and be detected, right? And maybe 10 months later, Hank called us in. There were 3 of us who signed up to be his graduate students and said, well, I came here with a promise of a tenure position. He was a visiting professor at that time, but this department that was really heavy on nuclear physics didn't really respect these guys in the corner Ed Ewing, Hans Deymelt, and Hank Silsby. So he was going to leave, and we'd have to go look for somebody else to work for. And so I guess I was, I got a, what are they called? Maybe an NSF pre-doctoral fellowship for 1 year when I just kind of looked around and took courses, and finally signed up with Ed Ewing to do an NMR. And this was a lab in which they had made a name for themselves studying hydrogen bonded ferroelectrics, right? So these are crystals in which the ferroelectricity is generated by kind of driving the electron to one end of a hydrogen bond where the bonds are slightly angled. And so that if you're at one end, you're lower position and whatnot, so you can create polarization that's kind of perpendicular to these bonds. A typical example of a hydrogen bonded ferroelectric is KH2PO4, as opposed to barium nitrate or something like that. So, but, so this is kind of interesting. I mean, Ed Ewing was a theoretical physicist from the 30s. He wrote a famous paper on vacuum polarization while he was in Germany in the 30s. He worked with George Uhlenbeck, who's the guy on the left there. And this picture must have been taken in the, I think, maybe late 40s, because the guy who's second from the right is T.D. Lee, and he hadn't won, he has a name tag on, which means that he hadn't won his Nobel Prize yet, right? So, but I couldn't get a date on this. I just got it from some website like AIP history or something like that. Anyway, Ed was a theorist. I mean, he did vacuum polarization in the early days of quantum mechanics. And then he was in Second World War, during Second World War, he did radar studies. And as with many other people who came out of Second World War knowing radar, he wanted to do magnetic resonance. And that's what his lab did the rest of his career for the next 30 years or something. But he was always a theorist. And so when you sign up to work with him, you go have a conversation with him, a very thorough one, maybe 2 hours or something like that, and he'll outline a project that he had in mind for you, which is strictly in terms of physics, not how to make that measurement, right? And then you go back to the lab, and all the other graduate students gather around you and say, oh, what did Ed suggest you do? And then they all pitch in to make a suggestion about, okay, well, maybe you should make a measurement this way. And in those years, what that meant was not what experiment you should do on this machine, but how to make the machine to do the experiment, right? And what he suggested was, he cited a paper claiming that for certain systems, the magnetization recovery after you saturate the system had a square root of time dependence instead of an exponential dependence. And to this day, I'm kind of astonished that that was in Physical Review, because you can plot any recovery curve as a function of square root of t, and there's a straight section, right? So, I mean, I'm oversimplifying the problem, but Ed saw that there was a definite problem, and he said, why don't you build an experiment so that we can really diagnose any deviation from experimental recovery. And we all know that there's got to be deviation from exponential recovery, because just imagine, something with a spin temperature up here, and then you're going to have a paramagnetic impurity or something which wants to drain the spins to this level. Well, you can't have spin diffusion if the spin temperature is constant, right? You need a gradient before there's a diffusion. So you got to knock the corners off this distribution until you achieve some kind of a slope. Then you can have exponential decay where you can have spin diffusion and the whole spin temperature changes. And clearly, in order to see this effect at the impurity, you need a lot of impurities, because if it's a part per million, chances are it's just going to affect a very small fraction of the total, and you're not going to see it. Anyway, so that's the project he assigned to me. And so, yeah, I say here that there are lots of words in here because I gave this talk in Paris, and I've always been told that, you know, people for whom English is a second or third language, and I was one at one time, have a hard time with these talks. So I try to put a lot of things in the words. So you guys don't have to read and understand all of it, but that's why they're there. And so the last sentence says that I built things for almost 6 years and did the experiment in 2 months or something like that, right? The other thing that's notable in my experience is that, you know, I was fully immersed in doing this for 6 years or something like that. I never knew what the outside world was like. And so I didn't know how unique this experiment was or the knowledge was. I mean, I should have figured it out because there's hardly any reference on how to do pulse NMR in those years. Be that as it may, I didn't. And so this happens to be the only photograph I have left, or maybe took, of any of the experiments. Whereas these days, we take pictures of it all the time. So that's the probe I made with 1/4-inch thick brass plates. And the thing that's notable is that it's a cross-coil experiment, right? And so this thing here. And that's because no one at that time knew how to make a single coil pulse probe. The marginal oscillator experiments were done with a single coil because all you're doing is making a tank circuit, watching it oscillate, and then when you go through resonance, the oscillation changes. But for a pulse experiment, you needed a cross coil or some kind of a bridge. You could build an RF bridge and then see a resonance in one arm of it. The problem with that is that you balance the bridge so there's no output, and then when there's a resonance, there's output. Well, if the bridge goes off balance by the temperature changing by 1/10 of a degree or something, it gives you a signal. So bridges were really hard to use. So we tended to do the cross coil experiment like that. So here's a transmitter coil, which our Helmholtz is on outside, and then the receive coil that's in the center. And I guess, let's see, this must be the transmit line, that's the receive line, and you tuned it with a capacitor. And the nice thing about that is that you can tune it over a large frequency range. And as you'll see, I wanted to do that in order to, there's a lot to be gained by being able to change frequency in an NMR experiment. And people don't do that very often anymore because you have a superconducting magnet and you aren't going to change the field on it, right? Whereas we used to have electromagnets and you can tune it to any field you wanted. By the same time, the electronics were primitive and it was hard to sweep the frequency. So we tended to always sweep the field. So this is the Lowenthal experiment that showed that you could use cross diodes and have a single coil experiment. And that came after I finished the thesis. So it didn't do me any good. But I mean, so this thing has really revolutionized how you do the experiments, and it's so simple, right? Whereas to make a cross coil experiment, it's more than twice as hard to have the two coils. So here's a circuit or a block diagram of the instrument I built, and it doesn't look spectacularly different from what we use now, right? It doesn't have a computer, and that's the main, and it doesn't have a digitizer and whatnot. But otherwise, it's exactly the same. It has a transmitter, it has a receiver, and and I just noticed before the talk that somehow or another the intensity is not uniform and things are really faint over here. But this is E, which is the transmitter output to the coil. And this is a high impedance circuit. Well, I mean, a transmitter had a vacuum tube. And so that's like a high impedance device. We're talking about 1,000 volts or something like that on it with a fairly small amount of current and into a parallel resonance circuit here. And so here are the parameters, typical parameters of this transmitter pulse. And it says 6,000 volts right here, peak to peak, right? So we're dealing with something totally different from what we're used to feeling. These days, it's a much lower voltage and a lot of current. Does the same thing because you just want to generate a lot of current in the transmitter coil or the NMR coil. So we got actually, so aside, I'm not sure it was a benefit, but the effect of all this is that we got pretty good at working with high voltages, and high voltages as opposed to high current involves special caution, right? And I remember that this final phase, the last connection to the probe was made with a wooden box for installation, and everything was insulated, right? So the box kept you safe. And then I had a potentiometer to adjust the height of the transmitter pulse. And I was kind of, and so the potentiometer shaft was sawed off, and then it had an adapter for maybe a plastic or a wooden shaft that came out of the box, so you'd be safe. And one time I got this big shock because the set screw that held the plastic piece onto the metal shaft did not come out to the, in our world. It was recessed in this, the sleeve of the plastic shaft, but the voltage is high enough that my thumb got over it, and it just arced over to my thumb and made a pretty good hole in it, and it kind of smelled it spread the smell of burning flesh in the lab, right? And so it's pretty sobering. Yeah, right. And then the other thing to note, as I told you, is that it's a total lack of signal acquisition system. I mean, it came out on an oscilloscope, and then you took a picture. You either looked at it and wrote it down in a notebook, or you took Polaroid prints, and you developed techniques like setting the intensity of the oscilloscope scan to such a value that it barely showed, and you make multiple exposures so that when those lines overlap, it'd be brighter, right? And so it's a analog signal averaging method. I mean, we're doing everything. And then if every data set was taken with a Polaroid print, you pull the print off the camera and you put a fixer on it, and then you put it on your desk and it curls up. And so if you do a year of experiments, which I didn't do, your desk is just full of these curled up pieces of paper, and you have to write on the back what you did, right? And you're always looking, it's a mess, but science got done just fine. Yeah, so here's a block diagram of the pulse sequence generator. And this is just to emphasize how primitive things are. So functionally, this is pretty easy to understand. I mean, you send the pulse in here to start a sequence of things, and these are outputs to various things. I think this one of these must be the transmitter or something like that. So these U's are what we call univibrators. They're just flip-flops that have their own time constants. So you trigger it and it flips, and then it flops at a different time. The thing to realize is that each one of those units required 2 vacuum tubes, right? So at any given time, there's current through one of them, the other one is off, and then when it flips, the current goes through the other one, and then it flops. And so, and we're talking about something this high and this big around, 2 of those for each one of those boxes. And then every one of these, that's a cathode follower. So that's for impedance matching later. And each one of those with a tube. So I don't know, 2, 4, 6, 8, 10. So this might be 25 or 30 tubes or something on a chassis like that. And we would have a signal, we would generate a pulse sequence, like maybe a comb of 8 pulses, 8 90-degree pulses to saturate the spins. So you place them farther apart than T2 and much shorter than T1. And so you give it a 90 and things spread out, give it another 90 and things spread out. And after 8 of them, the spins are full, unipolar, pointing every which way, right? And then, so this thing is a counter. So I guess you need 2, 4, 8, 16. So you need like 3 or 4 pairs of things that flip to count. And then, let's see, there must be an output. All right, so here's an output that feeds back to here. So this is a loop that ran like that. And it would run until this thing counts to whatever you programmed it for 8 pulses or something like that. And so I had let's say a comb of 8 pulses or 16 pulses. And then I would just repeat that the next time the external sources go. And then what I did is I triggered an oscilloscope on the first of the 8 pulses, so that, there's a group of 8 pulses, there's another group of 8 pulses with a delay, and I measured the free induction decay after the first of the 8 pulses, and then I just kept doing that. So the first pulse of the 8 doubled as the first scrambling pulse, but it also generated the signal to measure. And so the whole point of showing you this is it was really primitive, because you can do all that in a tip of a needle now, but not. And then I show this. So halfway through my project, there was a monumental paper by Gil Clark and RSI, and this was not a paper that talked about some aspect of the thing, but it was a treatise on how to do pulse NMR experiments, the whole thing. And so by then I built a bunch of different things, but I decided to build his receiver. And so this is a receiver. The thing to note is that, see, I wanted to do this experiment as a function of frequency, right? So these are tuning phases. So I had like 3 amplification stages, and they had to tune together to change frequencies on the pass band of what's being amplified. And then there, you can see that the individual things can be tuned with those. There were frequency bands that you switched with a switch, and then you could tune each one so that the different stages were at the same frequency. So, it's a mess, but the system did work. I did do variable frequency NMR, and I guess in this first presentation I prepared for the Paris meeting, I didn't have as much time as I have today. So I will tell you that the experiment worked, and we showed that indeed, if you look at a nuclei that's under the influence of one paramagnetic ion that's fairly small, not million spins, but maybe 1,000 spins, that you could indeed see the non-exponential recovery at first if you tune the system. The reason for having the ability to change the Larmor frequency is that you would like to tune the Larmor frequency to what the paramagnetic electron's doing. So we picked an S-state electron so that the flip rate is as slow as possible, right? So most electrons are going like crazy. It's way higher than the NMR frequency. And so there's a big mismatch. And we wanted to bring that down so that there'd be a better match, so that it was a better relaxation center. So I used S-state ions and picked Larmor frequencies that sort of match things. And where it matched, you actually got to see a non-exponential decay. But the non-exponential decay occurred for a pretty sharply defined set of parameters, which was a surprise. But we could get it and explain it. And I think I finished the equipment. Well, I'll throw in another bit of non-science here, just for your amusement. So Ed Ewing, my thesis advisor, you know, I told you he was a theoretician, and we were experimentalists, and he just gave us the project problems at the beginning, and then in some ways didn't help us much the rest of our time there. And we had lots of blackboards in the lab, and one of them had a strip across the top that was devoted to putting a check mark every time Ed Ewing was in the lab that year, right? And there may be 5 or 6 or 7 check marks or something like that. Well, one of them had a star on it because he came to get his glasses that he forgot. So in 1966, which was the year before I got out, okay, something like 1963, a bunch of us thought about going to go climb these mountains in Antarctica, and we tried getting support, logistic as well as money, and we failed, and so did every other group that tried, and so we bagged it. And the lesson there is that you won't succeed until you try. And what happened was in 1966, the State Department or I think, called up the American Alpine Club and said, whatever happened to those guys who wanted to go 3 years ago, because now the US government's ready to help them. And I think what's happened, of course, is that some person in the State Department's always looking out for news of having to do with American prestige or something like that, right? And somebody else was making noises about sending an expedition to go climb the last highest peak on a continent that had been unclimbed. So they had a couple of months to throw an expedition together from these groups that were interested 3 or 4 years earlier. And it wasn't enough time for most people to go. And I thought it sounded like a lifetime opportunity. I mean, I was never going to get another shot like that. And conveniently, Ed was on a sabbatical in Europe, right? And so I thought, well, I agonized over it and decided, okay, I'm going to go and then live with the consequences later. And I waited and wrote him a letter saying I'm doing that and left, right? And then when I came back, Ed was still on sabbatical, but I heard that he was really pretty irritated, but he took me back. And then I finished the construction. Maybe it was finished by then. I did the experiment and I wrote the thesis in the next 5 months or something. And Ed came back and everything worked out. And then in those years, you know, if you're a graduate student, you were a different kind of beast from a professor, right? So you didn't, it was like talking amongst different species or something. You hardly ever did it. The minute you got your PhD, you know, then everything is fine and you can talk like equals. And Ed told me that, well, he was really irritated, but somehow he let it go and everything worked out, right? And so that was great. So I have some, I'll finish this by showing you some other examples. Here are some old instruments that I used to use. And so there's a signal. So this is enough, close enough to Second World War that there are all these wartime equipment that we could use for NMR. So BC221 was one of the most prevalent signal sources. This is a Boonton grid dip meter. So there are still things you can buy called dip meters. They're not grid dip meters because they don't have any grids, right? Because they're solid state. but it's basically a tank circuit that's tunable with that knob. And if you put this coil next to some resonant circuit, enough energy is absorbed upon resonance of this other circuit to see this needle change, which is measuring the grid current of an oscillator. So it's like a marginal oscillator. And then when you transfer energy, RF energy, you can actually see it. So that tells you the resonance frequency of a tank circuit non-interactively. You don't have to connect the wire to it to change things. So it's kind of a neat thing. And you can even use it as an NMR device. You can take what you do is you change these coils with a fixed set of variable capacitor to change the frequency range. And the highest frequency is gotten with that short stubby coil. And if you use that and get a piece of cobalt and put this thing right next to it, you can actually see a resonance at 213.1 megahertz. So you can do NMR with just that thing. I mean, it's an anti-ferromagnet, so there's enough magnetic field in the cobalt. You don't need an external magnet. Let's see. All right. So I'm just throwing out random things here. So I was at Los Alamos in 1969, and this photo is of Nick Matlioff showing Ronald Nyholm this DP60, which is a CW NMR device that I was charged with putting together. I got out of University of Washington, and once again, I didn't plan on getting out so quick or something like quickly. So I had to scramble around for a job. I took a postdoc job at Los Alamos under an interesting guy named Eugene Robinson. And when I came for an interview, I met him, and he didn't say hello. He didn't say, how was the trip? He just started telling me about what he wanted me to do. And so this guy had no social grace whatsoever, but he was a very successful group leader. And it's one of these guys who, I mean, in fact, before I went, I talked with Greg Dash, who's a very good physicist at University of Washington, who'd been at Los Alamos. And I asked him, who is this Eugene Robinson who wants to interview me? And he took a deep breath and kind of sat down and then told me to sit down. And for the next half hour, he told me about Eugene Robinson. And the gist of it was that he was a guy with no social skills whatsoever. And maybe 49% of the people at the lab in the town detested the guy, and 51% thought he was a genius, right? And I should definitely go see him. What he told me was that Los Alamos has a very good postdoc program with good mentors. He wasn't able to offer me that at all, but he was going to use the postdoc mechanism to hire me if I wanted to come to put this DP60 together, which was in boxes that some other division had bought, and it was too complicated for them to use. So they put them back in boxes. And so he led a group of synthetic chemists, synthetic actinide chemists. They're making things that are just unbelievable to the chemical world, right? Because you're talking about 5f electrons in the actinide series at the bottom of the periodic table. So they're not, those orbitals aren't cubic orientation. They point every which way. So you can make crystals of really odd space groups. And they're making these brand new things all over the place and publishing them. And Robbie thought, instead of just making the things, he should collect people who can characterize a thing before they're given away, right? So he'd gotten an infrared spectroscopy, he'd gotten crystallographers, and he was lacking NMR, and he wanted me to come and put that equipment together. And if I did, he would pay me for the full 2-year term for a postdoc, and he would write me a good recommendation. And I thought, gee, what an odd offer. I went on to Salt Lake City to have an interview at University of Utah in June of '67. And it was over 100 degrees, no one had air conditioning. We had dinner at somebody's house and half naked. And I thought, I'm not going to come here. So I went to Los Alamos and I put that thing together. That's the DP60. They hired Nick Matweoff, who was the guy sitting down, to lead the NMR effort. And I was free to leave after 2 years. And then Robbie came to me one time after I started interviewing and said, I don't know what's happening, but I have orders from higher up that I should offer you a job here. And I took it and I stayed another 15 years or something like that. And, people are going to ask you what kind of talk you went to, and just tell them you learned all kinds of miscellaneous stories, right? So a couple of years later, I saw somebody, Eric Jones, who was a physicist at Sandia in the same town. And he said, hey, I gave a colloquium at Stanford, and he was an NMR guy before me at University of Washington. And this old man came up afterwards. The talk was on some CW NMR of intermetallic compounds. And he asked me, he introduced himself as Robert Fowler from Los Alamos. And he said, what would it take us to be able to do work like that at Los Alamos? And Eric said, Eric was in the same group with Ed Ewing. He was ahead of me. So he said, I think, I know somebody at Los Alamos who can already do that stuff. And Robbie, my group leader, said he just got an order from above to make me an offer. And putting two and two together, I think Bob Fowler, who was a division leader on sabbatical, told Robbie to hire me. And so I stayed there the next 15 years, and that's the rest of the story. So here's a few other studies I did of some note. So this one is interesting because I had that CW NMR, right? I built it. And I was kind of cruising or coasting because I was a postdoc, I was going to leave, and I was looking for experiments to do. And somebody had a bottle of C13 enhanced potassium cyanide on his desk or something. And I saw that and I said, can I borrow that? I won't even take it out of the bottle. It was a very small bottle. And I stuck it in the NMR. And I could get a C13 signal. And I wanted to measure the relaxation time. Well, all right, so this thing says, this is from the article I wrote. It says relaxation rate measurements were made by adiabatic passage at 16 megahertz on a Varian DP60 spectrometer. The signal was observed in an oscilloscope while the passages were made by switching the precession field scanner ranges by hand. The time required to go through a null was measured with a stopwatch. All right, so it just so happened that the relaxation time was something that could be measured with a stopwatch. And so here's like a picture of the controls on the instrument for sweeping the field. Just remember, we're sweeping the field, not frequency. So it had a knob for percentage sweep, right? And then it had a knob for how far 100% was. So this part, it would sweep 100% would be twice as far in Gauss as here, 5 times as much, 10 times as much. And so I would set it so that the resonance was off center of the sweep. I mean, these sweeps would be symmetric. So it sweep around 0, like, this thing might be this times 1, and then this thing will sweep twice as far. And if I set the resonance here, I mean, if I set the field there and then switch this knob between this scale and this one, I actually sweep the field from this position to that position, right? So I'd set the resonance to be in between here, and I could just go back and forth at a reproducible rate. And this thing had a T1 just right, so that, if the first time I sweep, it would go like that, and let's say that's the positive direction on the output. And then if I immediately come back, it sweeps back like that, and I'll see the same peak come back across the screen the other way. However, if I wait so that the thing relaxes, then when I come back, it's going this way. And so that's a negative signal. So the peak will come back upside down. And if I time it right, I see nothing, right? Because the thing relaxes halfway, and when it comes back, there's no magnetization to sweep. So that way I could measure T1. And I think the T1 is something like, well, this is T1 half, but it's something like 5 seconds or 6 seconds, or, you know, depending on the temperature. And I could get the activation enthalpy and stuff like that. And so I should tell you, you know, this is a science, we should talk about the science a little bit. The CN molecule is just kind of rattling around in there, like, despite the fact that it's, you know, 2-atom molecule, the wave function makes it almost spherical. So it doesn't have any, it's not affected by a barrier, and it just spins around. And I think I forget, the slope gave you a activation enthalpy that was pretty small. I don't remember what it is. So let me finish off by.
Can you go back to that slide for 1 second? I think we should point out that that's JMR volume 1.
Oh, that's right. Yeah. Let's see, where was that?
Yeah.
Yep, that one.
Wow.
Yeah. Yeah, so, you know, this new fledgling journal started, and we said, we should send something in. Maybe it'll last, or maybe it won't. But so this is another compound that some chemists were making, KBIF6. And the amazing thing is, well, let's see, what do I say here? Signals NMR measurements were made with cross-coil spectrometer with a variant field regulated magnet, Torgerson radio frequency unit, a lock-in detector, and other standard wide-line spectrometer component. Dave Torgerson was an NMR guy at Iowa State, and he made this really neat CW NMR box. And it was marvelous. And some of us, there are a bunch of papers written with that thing. And then he passed away quite early. And so here's so you have to understand that CW NMR, which you use as a boxcar integrator, and you modulate the field on a scale small compared to the change in the line. So when the signal is changing a lot, when you modulate, the signal changes a lot. At the top of the peak, it doesn't change, right, when you scan that. So what you're doing is getting a derivative. So this is a derivative image, spectrum of the line. So the line is actually a trapezoid, right? So I had never seen a trapezoidal NMR line before, and no one else had either. And it turns out what this is an incompletely resolved 10-line spectrum, because bismuth is spin 9 halves. So there are 10, it's a 10-line thing. And if you incompletely resolve it, it looks like a square. And excuse me, you can get a coupling constant from that. And there are rules about how coupling constants are supposed to go along the vertical line in a periodic table, and the bismuth fluorine coupling looks just fine compared to the tin or whatever else that's in there. And then the one last thing I did with that same system was to change the Nmr frequency. So at high enough frequency, you got that rectangle right there. And then as you go down, you got this thing all messed up. And so you go from 40 megahertz to, I think, 2 megahertz or something like that. And what you're doing is that you're changing the fraction of the dipolar term to the quadrupolar term by just reducing the dipolar term. So the quadrupolar term is getting much more important. And then so you get the quadrupole constant, you can get the sine of the quadrupole moment and stuff like that. And that was all done. Miscellaneous Adventures, I'm almost done here. So in the 1980s, a couple of us went to Siberia a couple of times. This is the beginning of the unwinding of a 100-meter diameter NMR coil. So a guy stands in the middle of the field with a 50-meter wire, and then the driver has the other end of it in his hand. And you can't see it, but there's a wire coming off the back end of that truck as it's making this 100-meter loop. And they're the guys who make the, water measurement in Earth's magnetic field with a 100-meter diameter coil. So they're looking 50 meters down or something. You do this early in the morning and then set up picnic tables and play cards or have meals or whatever. And by evening, you might have a pretty good signal, right? And then you put everything away and go home. So that was quite an adventure. And this is the last experiment I described to you. This thing is about 6 meters. Is that right? Yeah, 6 meters across. And well, I say, what is it? And that's how it's used. It's a helicopter-borne NMR coil at Earth's field. And it was used to detect the presence of, I think, like 5 millimeters of oil that might have leaked from some underwater oil well and got caught under 3 feet of Arctic sea ice. And so the coil would be put on top of the Arctic sea ice to detect this little bit of oil. And the big challenge was not the detection sensitivity, but the water suppression in the absence of any chemical shift, right? And we managed to do that just fine. And the last picture I have is Matt Augustine. So this thing is one of the single-sided boxes we made where you can put a watermelon on top and get an NMR signal or whatever. He's got it on a barrel of tomato sauce. So when a tomato sauce goes bad, the fibers separate from the liquid and the liquid ends up on right next to the wall. So the relaxation time changes and he can detect that. So it's basically a way to see the spoilage amongst a lot of cans that are being stored. Larry's seen this, but so this is such an appropriate thing, but it was sent from Erwin Hahn to Matt at UC Davis as a spin argument. The original intent of this guy, Bruno, was not for this. So this handwriting, we don't know whose it is, but it was converted for an argument about NMR. And it is, NMR is indeed useful and fun. And thank you very much for listening.